Alright, so this is homework number 4, question 8, in which we're given this nice long equation right there, and coupled with this nice table with 4 trials, molarities of the 2 reagents, and the initial rate of the reaction. It's 4 sub-questions, but it should go very quickly because they're all very nicely related to one another. So the first question is asking about the order of the reaction in terms of each of the reagents and total. So for this one you need to look at the chart to be able to see how the change in molarity of the reagents changes the rate of the reaction. And it's actually fairly simple. First you want to look at it in terms of the first reagent, so you want to look at 2 trials in which the second reagent has the same molarity but first reagent changes. So here I'm going to take trials 1 and 4 because the second reagent stays at 0.1 molar and the first reagent changes from 0.1 to 0.2. So as the molarity of the first reagent doubles, the initial rate goes from 1.3 to 2.6, also doubling. So you know that the change in rate, the change in rate and the change in molarity have a 1-to-1 relationship, which means it's first order. And now we look at the second reagent, the C2O4 4-, and again you want to look at 2 trials in which this one changes and this one stays the same. So here I'm going to look at trials 1 and 2, where the C2O4 doubles and the mercury chloride stays the same. This time, however, while the molarity of the second reagent doubles, the rate actually quadruples, changes 4-fold. So here we have this 2 to 4 relationship, which is a square, because 2 squared is 4, so that's second order. Now to find the total is actually easier than all of this. You just add them up, and the total rate of the total reaction order is third. Which brings us straight to the second question, which is to find the rate equation. So first you write out this very simple, basic, it doesn't really mean anything, rate equation, which is just rate is equal to the rate constant K times molarity of A, X, B, Y. Theoretically you could have like a million different letters here, but there's really no point in writing out all of that because we only need the 2. Now you just need to define A and B to be able to find X and Y. So let's say A is the first reagent, that's the mercury chloride, and that B is the second reagent, that's the C2O4 4-. Now the X and the Y are just the order of the reaction in terms of A and B. And those we actually have up here. So we know that X is the rate of the order of the HgCl2, which is 1, and Y is the same for the second reagent, and that's 2. So you just go ahead and plug all that stuff into the equation written right up here, and you have the rate is equal to K HgCl2 to the first, and C2O4 4- squared. And that's all done. Now for 3, they want you to actually determine the numerical value of K, which on its own would be a somewhat daunting question, just given this information up here. But since they have taken you through it step by step, it's actually just as simple as plugging some numbers into the equation you've already determined right here. To make this as easy as possible, I would suggest just going with the top one, because dealing with 1s is a lot easier than dealing with a 2 and all this nonsense. So just go ahead and plug the rate into R, which is 1.3 times 10 to the negative 7th, and then go ahead and plug in these molarities right there into the equation right here, just like that. And then you go and do some basic multiplication and division and whatnot, and you get K is equal to 0.00013, which, if you want to, I suppose you can rewrite it in scientific notation, with that being 10 to the negative 4th. So 1.3 times 10 to the negative 4th, which is wonderful. Now we have a value for K, which is actually a pretty powerful concept, and very important because it comes up on quizzes all the time. The fourth question is, when the concentrations of the both mercury 2 chloride and oxalate ion are 0.3 molar, what is the rate of the reaction? Which is literally the exact same question they just asked us. It's a matter of just plugging numbers into this equation you've already determined, this time with a different unknown. You're looking for R, but now you've already determined K, so you just plug that guy in right there, 1.3 times 10 to the negative fourth, and they give you the molarity they want. They want the 0.3 molar for each of them. So they're basically just want to see if you put 0.3 in here and 0.3 in there, what do you get out over here? And so that's what you're determining, which is super easy. You just plug them into this equation. You need R, you have K, and you have 0.3 to the first and 0.3 squared. And again, all you do is you just go through some really simple multiplication if you have a calculator, and it pops out with R equals 3.51 times 10 to the negative sixth, which you can then even go up and compare to your answers up here, and you can see that it's faster than most of these, which makes sense because as the molarity of each of the reagents increases, so does the rate of the reaction. So it really only makes sense that the reaction rate will increase as you increase from these 0.1 and 0.2 molarities in the given chart to the 0.3 molarity they want you to find at the end. And that's about that. Very easy, very simple, very straightforward.